All right, so previously we went over some pretty kind of complicated mind-breaking stuff. I won't be very strict on your kind of understanding that material, but everything kind of below this you really want to know well. So remember, the Schrodinger equation tells us about the energy of an electron and approximate location of an electron. And this approximate location of electron is what we call an orbital. And so an orbital, you can think of that kind of as the home of the electron, where the electron is most likely found. And so it gives us this information about energy and location in terms of quantum numbers. So there's four main quantum numbers that we'll go over. First up is the principal quantum number. This gets the symbol a lowercase n. And what the principal quantum number tells you is the overall size and energy of an orbital. So if we think back to our previous picture, right, we said energy, n equals 1, n equals 2, n equals 3, so on and so forth, right? And you can take a picture, think about what it means in terms of the Bohr model. It's not totally accurate, but it's pretty close. You have n equals 1 here, and as we get further out, we get higher energy and our orbitals get bigger. So as n increases, size increases, and the energy of that orbital increases, and thus the energy of that thing itself increases. You can find the energy of these orbitals exactly through the use of this equation. One over n squared, where n is just your number, right? First orbital, second orbital, that kind of thing. I won't ask you to do really anything here, but in case you're interested in. And then in terms of the values of the principal quantum number, n is a non-zero integer. So n can be something like 1, 2, 3, 4, 5. It can be any whole number, but it can't be 0. And again, what it tells us is the overall size and energy of the orbital. So that's our first quantum number. Next up is the angular momentum. Quantum number. And this gets the symbol of a cursive L, a lowercase cursive L. And so this tells us the shape of an orbital. An L can have values of 0 all the way up to n minus 1, and they all must be integers. So the value of L is dependent on n. So for example, if n is equal to 4, L can be 0 up to n minus 1. So n minus 1 would be 3 here, right? 4 minus 1 is 3. So L can be 3, it can be 2, it can be 1, it can be 0. Another example, if n equals 2, think about what L can be. The correct answer is L can either be 1 or it can be 0. And so when we're talking about the energy of the orbital, this n gives us the overall size and the overall energy of the orbital, but it's actually a little bit more complicated than that. If we think about n here, right, so n equals 1 here, n equals 2 here, n equals, let's move this 2 up a little bit further, 2 here, and then n equals 3 here, these energy levels actually can split. And so here we can have n and then L. And so this will split into one of these. This 2 can actually split into 2 different ones. And then this 3 can actually split into 3 different ones. And you can see we designate this by the N and then the L. But that can get very confusing because, then your numbers would be like 1, 2, 1, 4, something like that. And so what we do with L is we give it a letter designation. And so it's not too bad, right? L is generally 0, 1, 2, or 3. We won't go beyond L equaling 3 in this class. It's not really practical. And so basically you just have to know the letters. Instead of saying L is equal to 0, we say that it's an S orbital. Instead of saying L is equal to 1, we say it's a p orbital. Instead of saying L is equal to 2, we say it's a d orbital. And instead of saying L is equal to 3, we say it's an f orbital. And like we said, this designates the shape of the orbital. So we'll take a look at this a little later, deeper on, right? But the shape, basically, the S is a sphere. The P is this kind of dumbbell looking thing. The D is basically a four-leaf clover, or this kind of dumbbell looking thing with like a Saturn ring on it. And then F is kind of really hard to draw, but it's basically like two d orbitals. Right. And so if we kind of come back to this picture over here, we can designate these as N followed by L. And L, we're going to use the letter designation, right? So this would be a 1s orbital where N is equal to 1 and L is equal to 0. That's the only value L can have there. And then when we go up to N equals 2, L can equal 0 or 1. So this would be a 2s because you're in N equals 2. And then here S is, or L is 0. So we get S. And then up here, we're still in N equals 2, but now our L is equal to 1, so the letter is then P. And then repeat, right? We're in 3, but our L is 0, so it's 3S. We're still in N equals 3, but now our L is equal to 1, so it's P. And then finally, we're still in 3, but now our L is equal to 2, and so it's D. So these orbitals are called 1s, 2s, 2p, 3s, 3p, and 3d.